Hi, I'm Shanaz. Recall that in last lecture we proved that if we have an algebraic set, say X, in the affine n space, then this X is a closed subvariety. So this X is closed subvariety, which means this X is an irreducible algebraic set if and only if the ideal of X is a prime ideal in the polynomial ring. So this was the first result, and the second result was a short result, which says that if f is a polynomial in the polynomial ring in n variables, then if f is irreducible, this would imply the zeros of f is also irreducible. Now we want to show that every affine algebraic set, say X, in a unique way is the union of finitely many irreducible algebraic sets. So the idea, the idea is that in such cases we will be able to restrict ourselves to studying each of the pieces separately. So that is the idea behind studying these algebraic sets. We have uh, the following definition here. So, so any so a topological space, say X, is called Noetherian. If and only if, so if and only if every descending chain say X, which contains X1, which contains X2, and so on, of closed subsets of X becomes stationary. Now by stationary we mean that that is there exists some natural number n in n such that this x sub n is equal to x sub n plus 1, this xn plus 2, and so on. So that is what we mean a topological space X to be Noetherian. Now we have a short result here. So um, any subspace, say Y of a Noetherian space, X is Noetherian. So let us write this way. So any subspace of a Noetherian topological space is Noetherian. Let us prove this one. So let us assume that the space X is Noetherian. This is a Noetherian topological space. So, and let Y be a subspace of X. Now by subspace we mean this Y is having the subspace topology induced from X. So and let Y be a subspace of X. So we have to prove this Y is Noetherian, i.e. we have to prove every descending chain of closure subsets of Y is stationary. So let us pick a descending chain of closure subsets of Y. So let Y which contains say Y1 which contains Y2 be a descending chain of closed subsets uh, of Y. Now since we have the subspace topology on Y, so therefore these closed subsets will look like. So note that we can write we can write each yi as y intersection xi, while xi is some closed set in X. So where xi is a closed subset of X. So now we can replace. So we can replace uh, say xi by say xi prime, where this x prime I prime is given like this. So it is given to be equal, I mean this is actually equal to the intersection of all xj's where j is less or equal to I. So if this is the case, so then we can write. So one can see over here these xi's, they will form a descending chain of closure subsets of X, because xi prime will contain the set xi plus 1 prime, because it is due to this fact that j is less or equal to I. So then we can write yi to be equal y intersection xi prime. It is straightforward. So this is true for all I. And also this x contains x1 prime contains x2 prime contains so on. So this is a chain of closed sets of X. So therefore this would imply, so therefore now X being Noetherian, that means this chain has to be stationary in X. So therefore uh, there exists n in n a positive integer such that this x n prime is equal to x n plus 1 prime is equal to x n plus 2 prime and so on. So this further implies that, so this uh, implies that This implies that yn is equal to yn plus 1 is equal to yn plus 2 is equal to so on. So this is by definition of these xi, by definition of these yi's. So we chose yi to be y intersection xi prime. So this means this chain is stable. It is stationary. So hence y is also Noetherian. Now we have one more small consequence, which says that every affine, the affine space an is itself Noetherian, of course, uh, with respect to the Zariski topology. So the space an, let us write this way: the affine space an is Noetherian with respect to the Zariski topology. Let us prove this. So now to prove this is Noetherian, let us pick some descending chain of uh, closed subsets of an. The Zariski closed subsets. So let an, which contains say x1, which contains x2, so on, be descending chain of closed subsets of an. So indeed these sets are closed with respect to the Zariski topology. So the underlying topology over here is the Zariski topology. So we don't mention it repeatedly. So if this is the case, these are the closed subsets. So they are also algebraic sets. So then by definition of a function I which takes a set, an algebraic set to the ideal. So then I of x1 is contained into I of x2, so on. So this is because this I is a decreasing function, inclusion reversing function. So then this is an ascending chain of ideals. So this is an ascending chain of ideals in the polynomial ring k x1 through xn. But one can note here this space over here, this ring over here is Noetherian because k is a field. So and hence Noetherian. So since the polynomial ring in n variables is Noetherian, this would imply this chain stabilizes after some time. So this chain is stationary. So since this is Noetherian, therefore the chain of ideals terminate. That is, there exists, that is, there exists n in n such that the ideal generated by, ideal of xn is same as ideal of xn plus 1 and so on. One can note here these sets being algebraic sets, then we know that a function z composite I is the identity mapping. So using the function z, we get, so that xi being, xi's being algebraic sets, we have zero set of the ideal of xi is same as the set xi for all I. So therefore we have the zero set of I of xn will be equal to the vanishing set of I of xn plus 1 and so on, or xn will be equal to xn plus 1 will be equal to so on. So this means this chain is stationary. So therefore the chain which goes like this is stationary. Hence, and the affine space AN is Noetherian. Let's move next page. Now we have the main result of this lecture, which states that we can write every Noetherian topological space as a finite union of irreducible closed sets. So the statement goes like this: every Noetherian, every Noetherian topological space say X can be decomposed or can be decomposed uniquely. So this is up to reordering or up to permutation as a finite union of, as a finite union of, let's mention the union as a finite union. So x goes like this: x1 union so on union xr of irreducible closed subsets such that no algebraic set contains the other, with xi not containing xj for all I not equal to j. So one should note here these closed sets are called the irreducible components of X. So let us mention over here the set I mean this is xi are called the irreducible components of x. So this result has two parts. First part is the existence. So this is the existence part. So now it is enough to prove the existence of a decomposition into finitely many irreducible closed subsets. So it is enough to prove the existence of a decomposition into finitely many irreducible closed subsets. So the condition xi not containing xj for I not equal to j will allow us to omit all xi's where xi's are inside xj for j not equal to I. So let's write this down. So the condition xi not containing xj will allow us to omit I mean all xi's with xi inside xj for I not equal to j. So I mean if in this decomposition some xi is contained in xj, this condition over here will allow us to throw away the xi and keep the xj. So because it won't I mean make any difference to the union, because if we throw out xi given that xi is inside xj, then by omitting xi will not affect the union. So now we proceed by so now we proceed by contradiction. I mean we assume x does not have such a decomposition. So assume that x uh, I mean x does not have such a decomposition. So then x is obviously reducible. Otherwise, if x is irreducible, then uh, x is itself it is irreducible decomposition. So then x is obviously reducible, which means we can write x as, so that is we can write x as the union of two proper closure subsets where that is called this y1 uh, where x1 and y1 are proper subsets of x, so are closed also. So note that both x one and x y1 cannot be decomposed into finitely many uh, closed irreducible subsets. Otherwise, X has a decomposition into finitely many closed irreducible subsets. So, so note that uh, X1 and Y1 cannot be cannot be both. So can not. So note that X1 and Y1 cannot be both. So let us write this way. So note that both X1 and Y1 cannot be decomposed into finitely many or finitely many closed irreducible subsets, because otherwise X has a decomposition into finitely many irreducible subsets. So it is not the case because we have assumed otherwise. So therefore one of the two say X1, so therefore one of the two say X1 does not have a decomposition, does not have a decomposition into finitely many irreducible subsets. So this would imply this x1 is actually, I mean, this would imply this x1 is reducible, and which further implies we can write x1 as x2 union y2 for closed subsets, for closed proper subsets x2 and y2 of x1. So these are both proper. So if we continue this process, so again both these two not can be decomposed into finitely many irreducible subsets. So one of them has to be reducible. So we'll again assume x2 is reducible and the process will go on. So if we continue in this manner, so continuing in this way, uh, we obtain a chain. So we obtain a chain. So we started with x over here. So this x contains x1, then this x1 contains x2, and so on. So which does not terminate because due to our assumption. So this is a contradiction of X being Noetherian. So this is a contradiction of X being Noetherian. So this implies that we can, we can decompose X into finitely many irreducible closed subsets with this condition. Now, to prove the uniqueness, let us assume, so let X is equal to X1 union X2 union so on union XR, which is same is equal to Y1 union Y2 union so on union Y say S, be two decompositions, be two decompositions of X into into irreducible closed subsets. So note that we have, so we can note here we have this xi, we can write this xi as x intersection xi, but this xi is the union of these yi's. So this is actually union, say j goes from 1 to s of yi intersection xi. So this is same as union I goes from 1 to j goes from 1 to s xi intersection yj. So that is this. Uh, that is this xi is actually the finite union of these sets x1. I mean x1 intersection. Sorry, xi intersection y1 union xi intersection y2 union so on union xi intersection ys. So one can note here that these yi's are all uh, closed and this xi is also closed. So each intersection over here is uh, closed. So where each xi intersection yj is closed. Subset of xi. So this is true for all j equal to 1 to s. But xi is but xi is given to be irreducible. So this would imply xi will be equal to one of the one of these closed sets of this form. So this would imply that xi is so so this would imply, therefore there exists some, say, some j where 1 is lesser equal to j is lesser equal to s, such that this xi is equal to xi intersection say yj, that is, or this means xi is inside yj. So this is what we get. So similarly, uh, we can write, so like here we wrote xi here as this union. So similarly we can write yj as the union, say k goes from 1 to r, uh, I mean yj intersection xk, and by the same argument we get, and by the same argument, I mean there exists some, say, I mean some, I mean there is some k where 1 is less or equal to k is less or equal to r, such that this yj is actually equal to, I mean yj intersection xk. So this gives, so this implies, so this implies this yj is actually inside xk. So this will give this situation over here. So now if yj is contained in xk, uh, mm, so this would imply I will be equal to k, because, so, and hence this I is same as k. So because, so one can note over here, so we have xi which is contained in yj, so this is what we got here, and this yj is inside xk. So we have xi is inside xk, but these xi's, they are given to be irreducible. So that would imply these two are equal, and they will be equal only if I is equal to k. So and hence I is equal to k. Therefore, I mean, therefore we can write xi, which is same as uh, this xi is same as xi intersection yj, but I is same as equal to k, I is equal to k, so we can write this as xk intersection yj, because this I is same as k. So xk intersection yj, xk intersection yj is same as yj. So this gives this xi and yj, they are equal. So this means, so each xi is equal to one of the yj's. Similarly, we can show each yj is equal. So similarly, each yj is equal to mm, one of the xi. Therefore, these xi's are just a reordering of yj. Therefore, xi's are just a reordering of yj's. So this proves the result.